last time. There is a website. Jerry's got the handouts if you want to, and Jerry's right downstairs. You know where my office is now, just downstairs across from breakfast. So she can give you the handouts. You don't really have to read the handouts. In the handouts, there is a chapter 6, something labeled chapter 16. It's one of the first ones in the main handout. And just to explain that, well, it's probably more than 15 years ago now. The professors over mechanical engineering were writing a book on manufacturing, and so they needed a chapter on welding, and so they asked me to write it. And I took the lecture notes for this course home and just spent one day, kind of writing an outline of the whole course into one chapter. So chapter 16 is only 30 pages long. If you want to cut your reading real short, just read chapter 16. It's only 30 pages. It gives you a general outline of what we're going to do in the course. That's separate of the 3371 stuff on fracture mechanics and other stuff. The schedule that I hand out for the new people, the course is divided in two parts. The first one is what I call 337, which is welding and joining, and it's got we're going to go through cold welding and brazing and soldering and adhesive bonding, and then get into fusion welding and arc welding and lasers and electron beams and whatnot. The second part of the course is 12 lectures, and it's fracture mechanics, material selection, welding, metallurgy, and non-destructive evaluation. This year I'll lecture the 25 lectures in the 337. The 3371, which was originally designed for Navy students, I'll let you do that on the days that I have to be out of town. So the schedule that I handed out, there's 4 days that are underlined, and I happen to know I have to be out of town on, September 23rd and October 1st and October 7th and 8th. So you can watch the movie, and V will be here and it can show it to you. If you guys, small class, if you decide you don't want to come in those days and you want to watch it yourself, you can watch it online, okay, because that's what this stuff is being videotaped for, because other people take this course during the year. In any case, last time we kind of were going over the advantages and disadvantages of why you'd bother to study welding, and I'd come to everything. I don't remember if I'd discussed the ability to join materials limits the use of the materials. People will invent some new fancy material, and they don't worry about, they went through all this processing to get some sort of structure to the material, and then if you go and try to heat it up and melt it, you destroy everything they did, and so you've destroyed the properties. And in fact, that creates significant problems for a lot of other materials. Actually, I didn't bring it with me, but for example, the high strength steels for the Navy, they go through lots of fancy processing to get the high strength, and then when you try to do arc welding to that, you get more and more restrictive in the ways that you can weld those high strength steels, because they were more and more restrictive in getting the original strength to begin with. So it turns out some fairly simple things, like using aluminum in automobiles. I mean, we built all aluminum Duesenbergs in the 1930s. So it's not as if you can't build an aluminum vehicle. We did it for years. In fact, you can buy all aluminum vehicles now. Jaguar is making an all aluminum vehicle, and Audi's been making them for a few years. However, those are high-end vehicles. Anybody can make something. I mean, we've been making all aluminum airplanes for years, but they cost a little bit more than a Ford Taurus or something. Trying to make 250,000 automobiles a year out of aluminum gets to be a challenge, because you don't have welding processes that are as fast as you do in steel. In steel, we can use resistance spot welding, and resistance spot welding is basically just it's actually invented by Elihu Thompson, who was a professor here at MIT in the 1880s. Actually, he was president of MIT for 1 year, I think around 1900 or somewhere. But basically, you take two sheets of metal and you have two copper electrodes that come in, you squeeze it between the two copper electrodes, and for about a third of a second you pass 10 or 20,000 amps through that little spot, and you will melt the material together, so far as that goes. I guess I can put it up there, but you're not going to see it very well, so I'll pass it around. Well, until you can't resistance spot weld aluminum with great reliability. The Nissan NSX 10, 15 years ago actually went to resistance spot welding of aluminum to put the all aluminum sports car together, and they got like 40 spot welds before they had to redress the copper tips. And that means you have to shut the whole line down. If you're going to build a Ford Taurus, you have 60 seconds at each station. If you're going to make 250,000 vehicles a year, you can figure it out for yourself. But if you go into automotive assembly plant, it's basically what they call the takt time, T-A-K-T, right? Takt time is about 60 seconds. So the cars move down this continuous line, and the workstation has 60 seconds to get all the work done at that particular station. Well, you have to have a rapid, inexpensive, reliable joining process, and we haven't had that for aluminum. Now, recently, I guess end of last week, I was visiting Ford and saw some of the things they're doing, and hopefully they're going to send me some samples, and I'll show those to you later in the term. And people are making progress on those things, but the three big problems in putting aluminum into automobiles, for example, are cost of the aluminum, forming of the aluminum, and welding of the aluminum. That's what makes it, that's what keeps aluminum from making much bigger inroads in the automotive market. Although we have seen in the last 10 years high-end vehicles that are all aluminum. And you get some pretty dramatic improvements. I think Ford was telling me that they built an all-aluminum Ford Taurus. This is back 10 or 15 years ago. They built 20 of these things. And they were, when they redesigned the whole car, because once you take out weight out of one part of the vehicle, you can lighten up the axles and put a smaller engine in. If you redesign the whole car on the lighter weight material, you can get the vehicle down to about 2,000 pounds rather than, what, 3,600 pounds for a Taurus or something. And that means that all of a sudden your mileage goes up to about 50 miles a gallon. And so you're up to the, you know, a Toyota Prius, or however they pronounce it, okay? You're up to those types of mileage levels. It's not the automotive companies wouldn't like to do it, but they can't do it for a $20,000 vehicle right now. You want to spend $40 or $50 or $60,000 for a vehicle the size of a Taurus, and you can get an all-aluminum vehicle. So there are limitations. That's one case where welding is one of the problems. Now, the other thing is, I mentioned before that welding was a relatively large fraction of the material's cost, and actually somewhere in here I have an estimate of what the, here it is, I'll write it down. Actually, it's a small group, we can probably read it here, I think. We'll see how it does up here. Lighten that up a little bit. Okay. So if I've got a large-scale structure, this could be a bridge or a ship or something, the materials costs are probably only 10 to 20% of the cost of the project. The highest materials cost of any major large-scale construction that I know of is putting in a pipeline. You put a pipeline, all you're doing is taking pipe that comes from the mill, burying it, welding it and burying it in the ground. 30% of the cost is material cost. The rest is digging the hole and everything else. Well, the materials cost here, most things like a bridge or a building might be 10 or 20%. The welding and joining could be 10 to 20% of the cost. Other fabrications, such as machining or forming or whatever, could be 10 to 20%. Non-destructive evaluation would be 10 or 20%. G&A, which is general and administrative, depending on the amount of engineering. If you're building a pressure vessel and things, this could be even high, the high end of that. Could be 20 or 30%. And then the profit can be either plus 10% or negative 10% if you add all these types of numbers up. But the point is, welding is a relatively large fraction of the cost. Typically, the fabrication is equal to the cost of the material in something. Most people, a lot of material scientists, don't realize that the material costs are not really the major cost of building something. It's all the other stuff, all the manufacturing costs that go into that. For example, just to build the steel frame for a Ford Taurus is about $500. They're going to sell the vehicle for $20,000. The most expensive part of the vehicle is the engine. Anybody know what the second most expensive part of the vehicle is? The seats. Okay. But actually, the even more expensive part of the vehicle, which is not in the vehicle, health insurance for the workers. So as I think Chrysler estimates $5,000 per vehicle is the cost of health insurance for the workers assembling the vehicle. So anyway, okay, so we've talked yesterday and today about the reasons you might want to study welding. Let's now talk about how welding occurs. And I, for the first half of this course, I basically like to use a theme. And this goes for cold welding, adhesive bonding, brazing, soldering. It goes all the way to fusion welding so far as that goes, but we'll start another kind of theme later. That there are two fundamental problems with trying to get things to stick together. Anybody know what those are before we begin? Because you haven't read chapter 16 yet. If you read chapter 16, that's where you get these themes. Well, in any case, I'll hold off. Well, I'll tell you right now. One is surface roughness and the other surface contamination. And we're going to talk about that. You're going to hear that for the next couple of weeks. But before we do that, let's talk about the relative strengths of bonds. If I were to try to bring two atoms together, and I think somewhere in here, I have, here it is. This is, if you go to a chemistry book, you can read about the Leonard-Jones potential, okay? The Leonard-Jones potential essentially assumes that if I take an atom and then I have another atom out at infinity and I bring the two of them together, if they want to bond together, there'll be a force of attraction or an energy of attraction, and the energy has to be negative to be attractive. The force of attraction will bring it in until you get to the minimum point of energy, and if force is just the derivative of energy with respect to distance, here's where you have zero force. The two atoms will have an equilibrium spacing of separation of A0. Typical type of notation in chemistry books. Okay, so I got an atom here in space, and I bring another atom together, and if they want to bond, then they will bond with whatever the type of bond strength is, and we'll talk about that. If they don't want to bond, what type? Rather than getting a solid or a liquid, I get a gas, right? If there's not enough energy in that bond to hold them together, then the two atoms will spread apart, and I end up with a gas. Okay. Now, helium is the easiest one because it's an ideal or a noble gas, and there is no real significant bonding. There actually is an energy of attraction between a nitrogen molecule and another nitrogen molecule. That's why when you cool it down to 77 Kelvin, you actually will form a liquid. There is some bond energy, but there's enough thermal energy above 77 Kelvin that it vaporizes and becomes a gas. So you may have some plot like this even for things that are gases, but if I had two atoms that didn't want to bond together, like two helium atoms, as I bring them together, there is not a strong energy of attraction. There's no energy of bonding, and therefore they form a gas. But most things, two iron atoms, two nitrogen molecules, will have some energy of attraction, and so this is the energy potential, and that's the force between them. Now, it turns out that this force can be of several types, and we can look at typical bond energies of these things. Here it is. Typical bond energy for primary bonds I don't remember how much I don't know how much chemistry you had, but ionic bonds, covalent bonds, and metallic bonds, three different types of bonding. Ionic bonding is basically electrostatic. You got sodium, you got chlorine, one's positive, one's negative. They come together, it's electrostatic attraction. Covalent is where they come together and they share electrons, and metallic is this thing where you end up with kind of an electron soup with all these atoms in some sort of lattice or whatever. In any case, the energy per atom is on the order of 1 to 3 electron volts. And I've done this in electron volts because we're talking per atom, and it's just easier to see it. That's primary bonding. And if we were talking about tungsten, we might be talking, it's on the order of 1 to 3 electron volts. I don't know, tungsten, which is the highest melting point, might be 3.5 electron volts. But it's going to be something on that order. Lead might be down here near 1, okay, because it melts at a low temperature. So the melting point is related to the strength of the bonds, but you can go through and look at the heats of formation and you can calculate that type of bond energy. Well, if that's the bond energy, which means that's essentially the depth of this potential well, you can integrate the force of attraction and figure out how much strength it would take if these things are together to pull them apart, because you have to get over this, you have to overcome this energy barrier. You have to add this much energy, you have to do this force times the distance, and you can integrate all that. And how much strength do you think you'd have for a primary bond? Anybody have an idea? People actually measured this in the 1950s. They made single crystals of iron that had no dislocations, and they found that the strength of these iron whiskers was about 2 million psi. So fundamentally, in fact, I guess I think this may be in your handouts if it's not. One student a couple of years ago asked me how you got that, and it turns out if you actually integrate all this stuff, you can do a calculation that shows that you'll get about, I calculated when I did it, 1.88 million psi is the strength of attraction between two iron atoms going through all this stuff. Now I did it in terms of surface energy that we might get to a little bit later, or we will get to a little bit later. But inherently, two atoms, when they come together, have a tremendous strength. But what keeps them from bonding? There's two things that keep them from bonding, and we already mentioned them. One is well, let me back up. People actually have done the experiments. They took gold and put it in an ultra-high vacuum system, so they got no surface contamination, and they broke the gold. They did it in a way so they could cleave the gold. They had atomically flat surfaces, and they put them back together, and they had about a third of the strength. They broke them and put them back together in an ultra-clean environment, and they found when those atoms came back together, they had about 1/3 the strength of the original gold bar. Okay, so you know right now, if I put my watch down on the table, it doesn't bond to the table. But if it weren't for two things, surface roughness and surface contamination. Well, the first one, that experiment with the gold, where they did it in ultra-high vacuum, and there is no surface contamination, you can think of as just surface roughness. Now, if I were to take a piece of metal that looks flat, put it down on the table, you say, what's the area of contact? Well, the area of contact, you say, is just that area, right? But that's not the area of contact. In fact, on an atomic scale, or even on other scales, this thing is a lot rougher than it appears to us. It may appear to us, with our eyes, to be nice and flat like this, but on an atomic scale, it actually is rough like this. And so if I take two rough surfaces on an atomic scale and put them and just drop them together, what's the area of contact? Well, there's space in between here, and it's only the mountain peaks that are touching each other, right? And so the true area of contact, we'll prove later, when you squeeze things back together, will never be more than about 1/3. And so when they actually do these experiments in an ultra-high vacuum and take crystals and cleave them and put them back together, they still have a problem. They only get about 1/3 the theoretical strength. Okay. The other problem is one of surface contamination. And the problem there is that we don't usually break things in an ultra-high vacuum. In fact, how high a vacuum do you have to have? Anybody know how long it takes at atmospheric pressure to form a monolayer of gas on the surface of something? I mean, I got gas molecules going all around this room, and they're hitting the surface of this thing. Turns out the average speed of the gas molecules in this room temperature, something on the order of 100, 200 meters per second. There's a distribution of speeds, but it's something on the order of 100 meters per second. So it's a good thing they're light, because if you're getting hit by these things, right, you'd really feel the impact, right? In any case, if you take that and you take the distance of separation, what's the average distance of separation between the gas molecules in this room? Anybody have an idea? They're relatively close. They're not touching. It's not like two balls touching. But it turns out, if I told you that the volume of, let's say, a liquid like water at room temperature versus a gas, a vapor, that ratio, the volume of the vapor over the volume of the liquid at room temperature for something that's an ideal gas, most things, it's something on the order of 500. There's a 500 to 1 increase if I took water or propane or something like that, and starts out as a liquid, and I just let it vaporize at room temperature. There's about a 500 to 1. So that means that the distance of the separation between the molecules is just the cube root of 500, approximately, which is about 8. So there's about 8 atomic distances between atoms in the gas molecule. Well, if I go back to my good old Leonard-Jones potential, it turns out this energy of attraction is an electrostatic attraction, and you get more than about 3 or 4 atomic distances away, and you're out practically at infinity. There's no energy of attraction left when you get 3 or 4 atomic distances away. The only real attraction is when these things get real, real close, within 1 or 2 atomic distances. Okay, so in the gas phase, there's not a lot of attraction to these things. But where was I? I was going to show you. So I've got these things going around at 100 meters a second, and the distance of separation is something on the order of 10 nanometers. Okay, 10 nanometers, so that's 10 to the minus 8 meters. So I've got these things going at 10 squared meters per second, and they got a distance of separation of 10 to the minus 8 meters. And that says that in 1 second, or no, not in a second, but these things are going to travel between collisions. I'm going to have something on the order of 10 to the minus 10 seconds before the 2 atoms are going to run into each other, right? That's kind of the mean time between things. Well, it turns out in order to get complete coverage of atoms on a completely clean surface, it's about 10 to the minus 8 seconds, because I got to have more than one collide. If I had some absolutely clean surface, in 10 to the minus 10 seconds, I might have some fraction of these things. Let's say 1% of the surface gets hit in 10 to the minus 10 seconds. Well, in 100 times that, I'll essentially fill up the whole thing. Or it turns out 100 or 1,000 times. It turns out that it takes, the reason I put this thing up, this is out of a book from NASA. The reference is STP 431 in 1967, and let me zoom in here. Zoom in. This is zoomed a little too far. It's called adhesion or cold welding of materials in space environments, and NASA put this stuff out back in 1967, or had a big workshop to do this. And so they're looking at, of course, NASA's interested in going into space back then, altitude in hundreds of thousands of feet, pressure millimeters of mercury, density of the molecules, mean free path, miles at 25 degrees C, miles inches at 25 degrees C, impingement rate, time to form a monolayer in seconds at 25 degrees C. If I'm at sea level over here, it's somewhere between 10 to the minus 8 and 10 to the minus 9 seconds. Okay? And you can get that just by knowing that the molecules, you could estimate that just knowing the molecules are going 100 or a couple hundred meters per second. What happened? Oops. Oh, I overdid the brightness. Oh well, sorry. So here's, I gotta get this thing working right. It's got a funny focus. Okay, so here's sea level, 10 to the minus 8, 10 to the minus 9 seconds. That's actually called 10 to the minus, the time to form a monolayer as a function of pressure is called the Langmuir. It has units of atmosphere seconds, because if I'm at a lower pressure, it takes longer time because I have fewer molecules, greater distance to separation. Okay, anybody know who Langmuir was? Beginning of the century, he was a physicist at General Electric Research Laboratories. He studied surface chemistry, and so the time to form a monolayer of surface contamination on something is called the Langmuir. And it's a function, it's just pressure times time. 10 to the minus 8 atmosphere seconds. So if I took a piece of chalk and I wanted to break it and then re-weld it, I could do that, but I got to put it back together very quickly, within 10 to the minus 8 seconds or less at atmospheric pressure. If I take a piece of gold and I do it in ultra-high vacuum, at 10 to the minus 12 atmospheres or so, I might have a couple of minutes I could wait and put it back together. And that's the type of experiment that people did. And the only problem was they had there was surface roughness, and they got about 1/3 the bond strength. With contamination, you find that you get screwed up. You can't put it back together quickly enough. So why was NASA spending millions of dollars studying surface contamination back in the early 60s? Well, it turns out in the first Mercury space flights, actually, they just barely got up to space, right? This was after Sputnik. They didn't even go. It was John Glenn on the third mission that went all the way around. But Alan Shepard, the first one to go up, basically just kind of went out and took off from Florida and landed in the Atlantic. He went up to above 100,000 feet, which is considered space, but he didn't last very long. Like a 15 or 20-minute flight. Okay, but what they found is they used graphite as the lubricant because it always worked real well on Earth. And this is the structure of graphite. It's a hexagonal close pack. You can tell this is graphite because the atoms are black, right? And it has a hexagonal close pack crystal structure. Now, it turns out on Earth at 0.2 of an atmosphere oxygen pressure, the basal planes of graphite, these nice flat planes, tend to absorb oxygen atoms. So if you want to think of these little things, which are the feet for this crystal model, I got it upside down, as oxygen atoms, they would absorb on the basal plane. It turns out when you get out into space, the oxygen atoms are no longer, well, there's a reduced oxygen pressure, and the reduced pressure of oxygen allows the oxygen atoms to be stripped off that basal plane. And graphite, which is a lubricant on Earth, in vacuum or in the absence of oxygen, becomes an abrasive. And so NASA found that they had switches and knobs and things that worked just fine on Earth with graphite as a lubricant, and they got up in space and things were sticking together. So it turns out welding, in a sense, is the opposite of lubrication. Lubrication, I'm trying to contaminate the surface with something, but in welding, I'm trying to get rid of the contamination to make a good bond. I have to get rid of the surface roughness, and I got to get rid of the surface contamination. I actually had this experience with one of the 13A students, Dan Reese, in 1983, was working on welding of titanium in my lab, and we had a glove box, and we used ultra pure argon with like 10 to the minus 15 parts, or it's actually, yeah, it's about 10 to the minus 12 parts per million, so it's like 10 to the minus 18 as a partial pressure of oxygen. And he had a dust buster as a vacuum cleaner inside this glove box, and he found that the brushes that ran the motor wore out in like 5 minutes. Why? Because they were graphite brushes. And the graphite brushes, you got in there with no oxygen inside the glove box right down here in the lab underneath us, and they wore out because the graphite was an abrasive. Well, that's why NASA was studying this, because NASA found out without the oxygen in the air, all kinds of things that didn't stick together before start to stick together. Certainly graphite's a good example of it. And if you actually look at that STP, NASA was looking at how mineral particles would stick together, because they realized, well, maybe that's why you don't have certain types of dust storms on other planets, because if there's not oxygen around, the mineral particles will stick together, and it turns out they do. So surface contamination is a significant issue. Now there are ways around the surface contamination problem for lubricants. One solution is to use not graphite as your lubricant, but to use molybdenum disulfide. And molybdenum disulfide has the exact same hexagonal crystal structure as graphite, but the sulfur atoms are bound to the molybdenum much more tightly than the oxygen atoms are bound to the carbon. And therefore, you can go to low pressures and the sulfur doesn't just go off into the vapor. So molybdenum disulfide, in fact, that was the solution that I told Dan when he came to me and told me his brushes were wearing out. I said, well, just coat them with a little bit of molybdenum disulfide. Okay? And that way he had a lubricant that was still there. So anyway, the point is atoms will bond, and they'll bond with tremendous strength, potentially, if you get them within 1 or 2 atomic distances of each other. If the primary bonds are 1 to 3 electron volts, and the hydrogen bonds are 0.3 electron volts, if these 1 to 3 electron volts will give me 2 million psi as a bond strength, well, all I really need are hydrogen and van der Waals bonds, and I'll get just as much strength out of van der Waals or a hydrogen bond as I get out of a regular piece of metal, right? Why does a regular piece of metal only have 200,000 or 100,000 strength? It's because you have these dislocations in the crystal that move through the crystal, right? And they weaken it. Without any dislocations in the crystal, iron whiskers have 2 million psi strength. That's the inherent strength of the bonds. You can calculate it. People have calculated it. Without dislocations, you would expect things to be 10 to 20 times stronger than they really are. Now, it turns out, where are we now? What is let's think about surface energy now. If I think of a surface, I can just have a bunch of atoms in a solid, and they will have bonds to the atoms underneath. And the whole thing wants to form a solid because there's an attractive force between all these atoms. I've got other atoms down here, right? But on the surface of the material, I have unsatisfied bonds. If I look at an atom here in the center, all 4 of the bonds are satisfied. Each one of those bonds reduces the energy of the system. That's why it condensed into a solid phase. There's an attractive force, and all 4 of the bonds in that little 2-dimensional crystal I've got right there are formed on that atom. But on this atom, only 3 bonds are formed. And same thing on this one. All the surface atoms have unsatisfied bonds. In fact, we call them dangling bonds in surface chemistry. You have these dangling bonds on the surface. And that leads to what we call surface energy. And it has units of joules per square meter, or ergs per centimeter squared, or it also has units of newtons per meter. Because the joule is just a Newton meter, so if I put in Newton meter and divide by meters squared, I end up with newtons per meter. Or dynes per centimeter. Well, these are energy units, so these are force units. Well, it turns out it's all equivalent. I just showed you the Leonard-Jones potential. And in one case, I can think of it as a force of pulling something apart. In the other case, I can think of it as an energy of attraction or an energy of separation or whatever, whichever way you're going. And I can look at the surface energy of a material, and it will tell me something about the strength of the bonds and how strongly it wants to bond to or pull away from something, bond to something. In fact, that's what this calculation was that I did when the student asked me one time in the class. I pointed out that the surface energy of iron is about 1.3 joules per meter squared. And I said that strength of those bonds will give you a strength without dislocations in the material of 2 million psi. He says, well, how do you prove that? Well, here's the Leonard-Jones potential. You got to integrate this area under the f dot dr, integral of f dot dr from 0 to infinity. And if you do that and you put in 1.3 joules per meter cubed as the surface energy, you get 2 million psi. Okay? So surface energy is related to bonding, strength. And if I now look at some typical surface energies of materials, I find they only vary about two orders of magnitude, which is not very much. Why it's only two orders of magnitude? Well, the primary bonds only vary by about a factor of 2 or 3. So, I'm sorry, it's only about 1 order of magnitude. It goes from about, at 25 degrees C, the surface energy of water is 72. They're using ergs per square centimeter as these units. So that would be 0.072 joules per square meter, okay, if you wanted to know the units. Copper is 1.43 joules per square meter, or 1430 ergs per square centimeter. And these are types of bond energies. Actually, there's only about 1 order of magnitude. It goes, actually, I guess it's less. Yeah, it's about an order of magnitude. It goes from 1/10 up to 1,000, or, it's a factor of 20 total. And why is the difference? Why is the difference here? Well, it turns out if I looked at covalently bonded materials, I would find that the covalently bonded materials tend to have energies. What do I have that's covalently bonded here on this list? Actually, I don't have any good covalently bonded things. Let's look at ionically bonded. If I look at sodium chloride crystal, 300. If I look at calcium carbonate crystal, it's partly covalent, partly ionic, 230. Calcium fluoride, 450. Lithium fluoride, 340. It's the ceramics and the organics tend to be around 200 or 300. The water, as a liquid, is hydrogen bonded. It's about 1/3 of the ionically bonded or covalently bonded. The metals are interesting because the metals have surface energies that are much higher than other primary bonds, and that's because for the covalent and the ionic materials, it's only about 1 or 1.5 atomic distances that an atom up here, some foreign atom, X, up here, will only see the electrostatic charge 1 or 2 layers deep. In a metal where the electrons are much more diffuse, then you'll actually get bonding 3 or 4 or 5 electron layers or atom layers deep. And so you have higher surface energies in metals, significantly higher surface energies in metals. The metals here, copper is over 1,000. Silver, platinum. If you look on here, if you look on the ones that are 1,000 or above, except for these very high melting ceramics, which have strong bonds because they're just very strongly bonded ceramics, the ones with the highest values tend to be metals. Okay? Metals have high surface energies. And that means that metals are going to want to bond strongly if you can get them clean, but it also means metals are going to be very easy to contaminate, and they're going to be hard to get clean, because if I create a new metal surface, it has 3 times as much surface energy that it wants to get some contaminant on there to lower its energy. Because when the contaminant comes to the surface, it's bonded to the surface and it lowers the energy of the system. It's a spontaneous process, right? So that's one of the problems. Well, aluminum, you want to clean the surface of the aluminum. You have to get rid of that aluminum oxide. The aluminum oxide is extremely stable. It's a problem with titanium. The titanium oxide is extremely stable. Now, it turns out in titanium you have an advantage, because if I heat the titanium up enough, titanium will dissolve its own oxide. Aluminum and magnesium will not dissolve their own oxide. The solubility of oxygen in metallic aluminum and magnesium is near 0. And as a result, those things, you have to get rid of the oxide layer. But that aluminum oxide melts at over 2000 C. Magnesium is 2800 C. So tremendous strength to that oxide layer, and it doesn't want, it's not easy to get rid of it. It turns out one of the ways you can get rid of it in cold welding, which is what I'm supposed to be talking about today. In cold welding, maybe one of the last things here. When we want to weld wires together, say aluminum wires, oh, here it is. One of the ways to do it is to just push them together and get a lot of shear. These are dies that are going to grab this aluminum wire right here, and they're going to kind of kink the wire sideways a little bit and just smash it together and shove it together and just keep doing it to shear away the aluminum oxide and get mechanical action shearing away the contaminant, getting enough deformation that I get 100% area of contact. And in fact, I've actually never seen the aluminum welded that way myself, but I just happen to have, as I was visiting a student the other day who works in a tantalum wire plant, and tantalum has a very tenacious tantalum oxide, so far as that goes. And this, they have it's right over here in Newton, Massachusetts, they have a big new wire plant for tantalum, and this is the tantalum wire that was welded in the same technique. And they just pushed it together, and you can see, I'll pass it around, you can see the ratcheting of this thing, and they finally made a weld.
Did they add any heat to that, or is it just
nope, it's all cold, purely cold. That is a cold pressure weld, no heat whatsoever. When it comes out of the machine, it might be warm to the touch because of all the mechanical work you put in it. And actually, somewhere in here, they then skive off the, they kind of grind off the stuff. Here's the actual welded part after they ground the stuff away. And they're going to run that through a wire drawing machine now. Okay, now they've welded it together. They essentially have a, well, the process, they used to have 20-pound spools of wire, or 20-pound rods of tantalum that come out of the way that you make the tantalum alloys. And they have a machine that will roll up 500-pound spools of wire. Well, they had to have a way to weld the 20-pound pieces together. And that's how they do it, okay? It's just cold welding, and you've gotten rid of both surface contamination, and you solve the problem of surface roughness because of this interfacial sliding.
So does the process itself, does it right heat?
It will, if you do it fast enough, but this is not really that fast. I mean, it might on the surface heat the thing up to 500 or even 1,000 degrees, but that doesn't affect tantalum in terms of mechanical properties or softening. Tantalum melts at 3,000 C. It doesn't recrystallize until 1,500 C. I never heated it up anywhere close to that. You're essentially doing this cold. In aluminum, you actually might get some softening of the aluminum, and you have to be careful. If you run that process too fast in aluminum, you're going to run into a problem because the aluminum may soften on you, and when you try to push it together, it's just going to smush, right? However, that smushing is something, you can say, why are we spending so much time on cold welding? Well, it illustrates the principle of bonding here. But it turns out we make more thermocompression welds than any other type of weld that I know of. This happens to be the bond, the wire bond for an integrated circuit. Now this one actually had a defect in it. But basically you start out with a little gold wire typically, or sometimes aluminum. Turns out gold and aluminum are the two easiest things to cold weld. Well, we just said aluminum has a tenacious oxide. Well, we're going to talk tomorrow about why aluminum actually turns out to be one of the easier things to cold weld. But gold, which doesn't have any oxide on the surface, is the easiest. And it turns out you just start out with a little wire, and you have a machine where you actually have a wire bonder, which costs about $50,000 and sits on a tabletop like this, and it's very precise. And when it runs, it's sort of like looking at a very high-speed sewing machine. And basically, it just takes that little wire and it pushes it right into the surface of the semiconductor chip. And it forms a ball on the end purely by just squeezing it into the surface, deforming it. Okay, I'll have some other pictures tomorrow to show this, but I basically, and we call it thermocompression bonding because they typically do it at about 300 to 600 degrees F. They get it warm, but only to drive off the moisture off the surface or any oils that might be on the surface. So it's slightly warm. It's not truly cold like the tantalum. But they take a wire like this and they just squeeze it, they just ram it into the flat surface and deform it out like this, and you end up with that type of thermocompression bond. And down here at this interface, I obviously got some shear as the material's flowing out on either side, right? And so the shear scrubs the surface here. It doesn't scrub it much over here. So the only real bonded area is probably right there. Doesn't really matter. Those wires are typically, nowadays, on the order of 20 to 25 microns. A thousandth of an inch is 25 microns. So these might be 8 ten-thousandths of an inch across. And you make these bonds at about 7 per second. It's kind of a typical, this thing's a humming away as a sewing machine. Okay? It's just kind of, just like a sewing machine, you have a little mechanical arm that kind of pushes the needle down into the thing. Well, here, you're pushing the wire into the surface, and then you're moving over, you know, just like the needle moves over. It's just like a sewing machine. It's just a $50,000 sewing machine. You know, actually, I was talking to someone this summer, and they were telling me they've gotten speeds up to 15 per second. But you actually get limited by the inertia of the head that you're moving, right? The mass of that head. And they, you know, you're machining the heads and for wire to hold wires and precision place them, and they're only 8 ten-thousandths of an inch in diameter. So you're talking some really precise machinery here to do this. But how many chips? I mean, some of this stuff in this course is to help you figure out how to estimate things. How many thermocompression bonds do we make in a year? Well, the semiconductor industry is probably a $200 billion industry. And a chip costs, well, some of the chips are just simple chips. I mean, a Pentium is going to be worth anywhere from $100 to $500. But other chips, a memory chip, is worth $3, right? So what do we want to pick as the value of a chip? I'm going to pick $20 as the average value of a semiconductor chip. And it turns out, how many bonds does it have? Well, we're going to talk about inputs and outputs probably tomorrow on electronic bonding and stuff. But let's say it's got 200 inputs and outputs. But I got 2 bonds for every one because I have to go from the chip carrier to the chip to make the connection, right? But I got 200 of these connections. I got about 400 connections, thermocompression bonds on every chip. So I got $200 billion divided by $20. That's 10 billion chips, right? Times, rather than 400, I'm just going to call it 500 bonds per chip. And I'm up to, this isn't large, yeah, this may be right. 5,000 billion bonds per year. 5 trillion bonds. What did I estimate last year? I don't remember. Somewhere in here. I'll find it. Oh, I estimated 50 trillion. Okay, I don't remember where I got my 50 trillion. Maybe I dropped a zero here. Who knows? So that's a lot. Okay. And the interesting thing about it is if one of them's bad out of 500, I got a bad chip, right? So the reliability has to be tremendous. This is, you know, it's a simple technology, but it's a critical technology to making all our semiconductor chips. So I'll talk to you tomorrow. See you tomorrow.